All right, today we're jumping headfirst into a real cosmic mystery. It's a story about the gorgeous final moments of stars, kind of like our own sun, and a light that's, well, it's both a guiding light and a total puzzle. So, the big question is, how do astronomers actually measure the universe using the last gasp of a dying star? But what happens if that last gasp doesn't play by the rules we think it should? Yeah, that's where things get really interesting. And that's the heart of our investigation today. So let's start at the beginning.
Okay, so to crack this case, we first have to get familiar with our main piece of evidence. And it's a big one. It's a cosmic measuring stick that literally lets us map out the entire universe.
So, picture this. When a star like our sun gets old and starts to run out of fuel, it doesn't explode in some huge supernova. Nope, it's much more elegant. It kind of sighs out its outer layers, puffing them into space. This beautiful, glowing cloud of gas is what we call a planetary nebula. And the tiny, super hot star core left in the middle, it acts like a spotlight, lighting up all that gas and making it glow like a giant cosmic neon sign. Just gorgeous. Now, here's what's so cool about them. For years, astronomers noticed something super useful. If you look at any galaxy, the brightest of these planetary nebula, they all seem to have the exact same peak brightness. It's like they have a built-in dimmer switch that stops at the same maximum setting. We call these standard candles. And think about it, that's an incredible tool, right? If you know the actual wattage of a light bulb, you can figure out how far away it is just by seeing how faint it looks. Same principle, but on a cosmic scale. Okay, and this is where our mystery really kicks into gear. Because, basic physics, the stuff we really trust, tells us that bigger, more massive stars should produce way brighter nebula. I mean, it just makes sense, right? More fuel, bigger engine, brighter light. But that's not what we see when we look out there, at all. It's like something is capping the brightness, a universal speed limit on how bright these things can get. The big question is, why? All right, every good detective story needs a prime suspect. And in this cosmic whodunit, the number one suspect is, well, it's dust. The leading theory has a fancy name, circumnebular extinction. But the idea is actually pretty simple. As that star is dying, it's not just breathing out gas. It's also kicking out tons and tons of dust. This dust creates this thick shroud all around the star. So when the nebula lights up in the middle, it's shining from inside its own dusty cocoon. It's basically its own built-in lampshade, dimming the light before we ever get a chance to see it. So here's the thinking, right? The more massive the star, the brighter the nebula it should make. But, and this is the key, the more massive the star, the more dust it probably creates too. So what if those two things perfectly cancel each other out? The extra brightness gets dimmed by the extra dust. It's a really elegant theory, right? It would perfectly explain that constant maximum brightness we see. But how on earth do you prove it? Well, you can't exactly go out and tinker with a galaxy in a lab. So scientists did the next best thing. They built their own digital universe inside a computer. They used this incredibly powerful simulation tool called the PIX framework. Seriously, just think of it like a virtual laboratory for the cosmos. It lets them cook up whole populations of stars, different ages, different sizes, the whole shebang. And then they just press fast forward to watch them evolve and see what kind of planetary nebulae pop out at the end. So their mission was pretty straightforward. Could they find the perfect recipe for how this dust works? Could they program a set of rules into their simulation that would make their fake nebulae behave exactly like the real ones? If they could pull that off, it would be a huge piece of evidence pointing right at dust as our culprit. So how'd they do? Well, at first, it looked like they'd cracked it. Case closed. And you can see their initial success right here. It's pretty amazing. After they fiddled with their dust recipe, the simulation, that's the solid line you see here, predicted this really clear relationship between a star's mass and how much dust dims its light. And then, look, they compared it to real observations, those are all the little dots, and it was a near-perfect match. I mean, wow. This was a huge deal. It felt like a breakthrough. The model worked. It seemed like this whole self-dimming dust idea was the answer to this decades-old puzzle. The prime suspect was about to be convicted. But, in science, just like in a good detective story, there's almost always a twist. And that's because when the scientists zoomed out, when they looked at the whole crime scene, not just one piece of evidence, their perfect theory started to unravel. So yeah, the model was great at explaining the average nebula. But was a dusty shroud really the final answer? Could it explain all the evidence we see out there? Let's look at the clues together. This here shows what their successful simulation predicted for a whole population of these nebulae. See how most of the simulated data points are all clustered down there at the bottom? The model basically said, okay, most nebula should have a pretty low amount of dust around them. But then they looked at the real universe. And, look at this. Sure, some of the real nebulae match up, but there's this huge group of them way up high, with way more dust than the model could ever account for. The simulation just couldn't make these super dusty nebula that we know are floating around out there. And the scientists who ran the study were totally upfront about it. They said it right in their paper. Despite everything they tried, their model couldn't reproduce the sheer number of super dusty nebulae we see in observations. There was a huge chunk of evidence their theory just couldn't explain. So what does this all mean? It means dust is definitely involved. It's at the scene of the crime, but it didn't act alone. Our prime suspect has an alibi. It couldn't have pulled this off by itself. So where do we go from here? Well, our investigation is far from over. In fact, we're left with a mystery that's even deeper and, honestly, way more exciting than the one we started with. We know dust is a key clue, but it seems there were accomplices, and the list of potential co-conspirators is pretty wild. We're talking about things like binary stars, two stars dancing around each other and messing things up, or weird objects called blue stragglers, or maybe even something as dramatic as two dead stars, white dwarfs, crashing into each other. Any of these could be the missing piece that's creating all that extra dust.
And you know what? This is what I absolutely love about science. They started with what seemed like a simple question. Why do these things all have the same max brightness? And the journey didn't end with a simple, tidy answer. Instead, it blew the case wide open, revealing a bunch of new, even more fascinating questions about how stars really live and die.
So, no, the case of the constant candle isn't closed, not by a long shot. It's only gotten deeper. And it really makes you think, doesn't it? If the final moments of a simple star can still be this puzzling, what other incredible secrets is the universe hiding, just waiting for us to ask the right questions?